Calculating the electric field of a simple, discrete point charge is a standard application of Coulomb's law. If you have the charge and the distance, the math is direct. However, real-world matter is rarely that simple. Most objects are continuous, which means we have to imagine breaking them down into an infinite number of microscopic volume elements just to begin a calculation. If you try to calculate the field of an asymmetrical blob using standard integration, you run into a mathematical wall. Because the shape is irregular, the distance and direction vectors change for every single point you measure. You're left with a calculus equation of overwhelming complexity. Attempting to solve these complex shapes through brute force integration is a mathematical trap, one that most students would prefer to avoid. Gauss's law provides a way around that trap. It relates the total electric flux passing through a closed surface directly to the charge enclosed within that boundary. Technically, this law is true for any closed surface, no matter how lumpy or irregular. But applying it to a chaotic shape doesn't actually simplify the work. The real power of the law appears only when the object has perfect physical symmetry. This is where we use a Gaussian surface, an imaginary 3D boundary that you draw specifically to mimic the shape of the charged object. When the boundary matches the symmetry, the integral dissolves. The problem shifts from high-level calculus to basic geometric area. Consider a classic textbook physics exam scenario: an infinitely long, thin, straight wire possessing a uniform electric charge. The geometry of the field is radial. Invisible field lines shoot straight outward in every direction from the central axis of the wire. To find the field strength, we need a 3D boundary enclosing this radial field. We wrap a translucent cylinder around the wire, our Gaussian surface. Because field lines are perpendicular to this curved wall, the field magnitude is constant across the entire surface. Since the field is constant, it can be pulled out of the integral. The math simplifies to the surface area of a cylinder, giving you the field value almost instantly. Now, let's look at a uniformly charged infinite plane sheet. In this case, the field lines are parallel. They shoot straight out from both sides of the sheet, never diverging. The ideal boundary here is a rectangular box that pierces through the sheet. The parallel field lines only pass through the two flat end caps. Since they run parallel to the side walls contribute nothing to the total flux. The resulting formula for the electric field reveals something counterintuitive. The final equation contains no variable for distance. For an infinite charged plane, the electric field strength remains the same whether you are 1 centimeter away or 1 kilometer away. Finally, we have a thin, hollow, spherical shell with a uniform charge. To find the field outside, we draw a larger sphere around the shell. From this external perspective, the math treats the shell as if all its charge were concentrated into a single point at its very center. But what happens to the field inside the hollow shell? We shrink the Gaussian surface inward to find out. Because this internal boundary encloses zero charge, Gauss's law dictates that the electric field inside the shell must be zero. This interior silence is the ultimate test of the inverse square law. If the electric force didn't weaken exactly by the square of the distance, the contributions from every part of the shell wouldn't perfectly cancel out. We've just mapped the forces of 3 complex objects without solving a single difficult integral. Gauss's law operates as a matching game of spatial dimensions, reducing an entire field of vectors down to simple surface area. When you are facing a continuous charge problem, you must always start by identifying the true symmetry of the object first. Success in electrostatics comes from looking past the variables and finding the symmetry that makes the math disappear.